Now that we have all the inputs and outputs, we are going to work on the logics to calculate the heating percentage. We need to do that separately for state off and state on. So first click on the off to highlight it. It will show the logics system will run when the system is off. For our control, when the system is off, we just output a heating percentage of 0, which is a constant. So we grab a constant float and connect it to the heating percentage output directly. So double click to change the name to off percentage. The present default value is by default 0. We don't need to change it. So we just connect it directly to the output. Now let's move on to the state of on. Click on to highlight it. We are going to use PID control. So under the group of control, we add a PID preprocessor and a PID block. I'll enlarge it a little bit so you can see it. So before I explain the parameters, I'll just connect all of them except set point and the process value. Those minimum tuning band to tuning band in PID, process range to process range, time constant to the same in PID. So basically just output, connect each output of PID preprocessor to the input of the PID block, right across, straight across, period to period, saturation time to saturation time. So now we can see that the preprocessor provides all those parameters to the PID block. What is the difference to using the default value in PID? The difference is that in the PID preprocessor, there are a lot of those values are calculated based on several common control loops. Now let's double click. We can double click on the preprocessor to see the parameters. The most important parameter here is the process ID, which defines what kind of process value you are going to control. So here, by default, it is zone temperature, which is the same as what we are doing in our example logic. Once this process ID is set, preprocessor will generate a set of values, including the integral time, saturation time, and all those settings, and supply them to the PID so that it will generate good control to a large majority of the control loops that is used to control zone temperature. We can click here to have a look at what kind of other options we have. So it covers most of the processes we use in the buildings, like airflow, which is used in VAV, discharge air temperature control, duct control, pump difference pressure and those things. But if your system is not covered here, it is a very specific application, then this PID preprocessor won't help very much. You will need to do manual tuning to get the optimum settings. You will need to set this standard tuning at 2 if you would like to use the parameters generated by the system associated with the process ID. If you set the standard tuning at false, it will allow you to enter the parameters of your own. So we will leave it at 2 here and then apply, close it. Now we are going to have a look at this PID block. Double click to show all the parameters. Now let's go through some of the important parameters here. So first is the low limit and high limit. Those are the limits for the output of the PID control, the present value here. For dampers percentage, it is 0 to 100. If it's airflow, for example, the VAV we worked on in the previous lab, you can put this low limit to the actual low limit of that VAV box and the high limit to the actual high limit of the VAV box and change the units accordingly. Offset, it is a constant value that is added to the sum of the proportional term, integral term, and derivative term used to generate the present value. It doesn't have any impact on the PID control itself. Direct acting, this is a very important parameter. We can set the values at true or false. Direct acting means that the actuator needs to increase its output when there is a positive error in the process variable. We can have an experiment later and change this direct acting to false and see how the system reacts. The next one is the adaptive tuning. This is Johnson Controls patented algorithm to do adaptive tuning, so we are not going to introduce it very much. Then we have process range. This process range is the range for the process variable. In our situation, it is the range of the zone temperature to get the heating output varying from 0 to 100. The parameters below are for the PID tuning. All those are for PID tuning, and they are from the PID preprocessor. The last one, reset tuning, if we set it at 2, it allows us to manually reset the tuning. That's all of the inputs of the PID block. We can expose all of those inputs and outputs if we'd like to. So we just apply and don't do any changes, then close it. How to expose those inputs and outputs? We just right click and click on the expose ports for connection. For example, if we are going to expose this direct acting and reset tuning, we just check the check marks and then click OK. Now we are going to do the connections. So we connect this room temperature set point to the set point of PID. Zone temperature, it is the process variable for the PID, and direct acting, it is a Boolean, and we can use a Boolean input. Just a jag1 Boolean input. Change the name to direct acting. And then connect it to the direct acting. We add another Boolean. For the reset tuning. So this is reset tuning. And let's check the default value is false. Okay, we can just use the default value and connect it to. So if we need to reset the tuning manually, we just change this value to true. For the PID preprocessor, we are going to expose the port for the. We can choose to change it, but since in our situation the process ID by default it is the same as our zone temperature control, so we are not going to expose this port. So we are almost set here. The next step is to connect the PID output to our output heating percentage. Okay, we now have finished all the programming. So this is the overall state control. This is the value when the system is off, and the logic when the system is on. Another thing to do is to connect the inputs and the outputs we just added. Go to connections, right click on zone temperature and connect it to the hardware input zone temperature. And the zone temperature set point, and connect it to zone temperature set point. And the output, we will connect it to the heating control output. Now we can start the simulation. Click on simulate, save changes, and check the startup value, auto temperature at 18, occupied, heater status at normal, set temperature at 22, zone temperature 20, auto lockout set point, we set it at 25 and click OK. So the system is now on because all the criteria to start the heating are met. And then let's have a look at the value. The heating percentage required is now 47.6. Let's wait a little bit to see how the system changes the value. So after some time, now it's increasing. Now let's change the direct acting to true and see what happens. Right click on direct acting, click commands, and then set the value to true. Click OK and send the value. And let's wait to see how the heating percentage output is reacting after we change the direct acting to true. Now it's decreasing. In most of our control loops, a process variable that is below the set point, which is a positive error, requires the actuator to increase its output. This type of output is known as reverse acting, which is the same as setting the direct acting at false. So when the room temperature is below the set point in our case, we will require a higher heat percentage output. So we should set the direct acting at false. So I'll change this back to false. Now you can build your own project and try to do some simulations, send different commands, and see how the system reacts. I will explain a little bit about how our example is similar to the Johnson Controls pre-engineered programs, so that we will be able to read their programs.